So, welcome to Nick Baines for his talk on using CAD CAM for designing and building locos. Thank you, Nick.
Right. Well, thank you very much, James. Good afternoon, everyone. Good morning, good evening, depending on which part of the world you're tuning in from. Um, as you can see, I've extended the title of this a little bit. The original title was CAD, and I've added CAD CAM for reasons that I hope will become apparent as we go through the presentation. But basically, they're two technologies which are not necessarily dependent on each other, but there are some very strong links between them. If you know anything about my O-gauge activities, you'll be aware that I've built quite a lot of 19th century prototype locomotives, and inevitably that means scratch building because the kits and the ready-to-run models just aren't available. When I had a real job to do, I was an engineering consultant, which meant that I could go into quite a number of different engineering companies, and I was very aware of the changes that were happening with the introduction of CAD and CAM technologies there. So when it became feasible to start using those in the hobby sector, I was really very interested to explore what could be done. And so this presentation is really about my experiences, which means that I'm only going to talk about the things I know about, and some of the other things I will not be talking about because I felt that I just didn't have enough information to be able to do that. Right, so to begin at the beginning, what do we mean by CAD and CAM? So CAD is computer-aided design, CAM is computer-aided manufacture. Some people call it computer-aided machining, but manufacture is a much more general sort of term. And I'm going to start off by talking about CAD, and then we'll move into CAM. And as I've already said, I hope that we'll be clear about the linkage between the two. So first of all, computer-aided design, which means that you can produce nice pictures of locomotives in various stages of construction, and you can look at the internals as well as the externals. And some people do seem to use it for no more than producing nice pictures, and good luck to them if that's what they want to do. But what I first of all want to do is to try to answer the question, well, what can you actually do with CAD, particularly in the context of our hobby and in the particular context of building locomotives? For the most part, not the only part, but for the most part, it's about making computer readable files which can then be transferred to CAM tools and CAM machines and processors in order to create parts. And the files are not meant to be human readable. And if you can read them at all, then you'll see that it's entirely gobbledygook, unless you happen to be a geek who has made a careful study of these things. The transfer of data from the CAD to the CAM is meant to be fairly seamless, and you're not meant to be able to do anything much with the intermediate file, even if you wanted to do so, which frankly you probably won't anyway. That's the main thing. That's what most people use CAM for. CAD, beg your pardon. You can do other things with it as well. For example, you can produce drawings which look very much like the drawings that a previous generation of draftsmen produced using pencils on drawing boards and T-squares and all the rest of it. Um, and if you want to make drawings of parts, which you can then take into the workshop and make using manual methods, it's perfectly fine. It's perfectly doable. I've done that myself. Not for every part, not on every occasion. If it's a very simple part, then I resort to the usual method of scribbling something on a piece of paper and working from there. If it's a complicated part, if it has to fit together closely with other parts, or if there's any particular features, then yep, sometimes I do a drawing like this, print it off and walk down, put it in the workshop and work from there. But the point about it is that this really emphasizes that we're talking here about the computer version of traditional technical drawing. So if you're familiar with technical drawing, if you learnt technical drawing way back when, this sort of thing would be very familiar to you. And the other thing that I found it useful for is identifying assembly problems. So here's a picture of a loco that I was building a while ago. And by making a model, a computer model that is, of the loco, I was able to identify some potential clashes. So for example, there's one highlighted here and over there. And that comes about because the back-to-back dimension of O gauge fine scale is actually smaller than it really ought to be. If you're modeling in scale 7, stop laughing now. This was fine scale. And well, if you draw the boiler and the firebox to scale dimensions, then of course you do get the problem that's highlighted there. The wheels end up running into those components, and we have to do something about it. I was sort of expecting that because I think most builders have encountered that problem at some time or another. One I wasn't expecting was that one that you can just see down there. For this particular model, I was hoping to use inside cranks from Laurie Griffin. They were a little bit over scale, unfortunately, which, you know, from the point of view of making the model go, really doesn't matter at all. And visually, I don't think it would be noticeable either. But unfortunately, lorries were just a little bit too big. And so that told me that I couldn't do that. I would actually have to make my own cranks, whether I liked it or not, if I wanted to continue with a boiler of scale dimensions. But the big problem was was this one here. So having identified the problem, what do we do about it? Well, a couple of options immediately sprang to mind. One is to make the boiler smaller than scale so that it actually fits between the wheels. And if you scale down the boiler, then of course you have to scale down the firebox as well. And to maintain the proportions of the loco, you have to scale down the smoke box. So actually, one large major component of the loco turns out to be smaller than it really should be. The alternative is to keep scale sizes here and cut a hole in the boiler and firebox in order to accommodate the wheel, and also cut the splasher back in order to fit over here. Of course, the splasher fits exactly as it should on the prototype. This one we have to start cutting back the splashers as well. So the question is, which is the better way to go? And ultimately, it's a personal decision. Um, this one I rejected because I thought that the whole proportions of the Loco just started looking wrong. The boiler should be bigger than it looks in this picture here. So I decided that having the splashers cut back was the only really visible downside to going this way, and that's the way that I decided to go. But the nice thing about using the CAD was that I could explore those two quickly and easily and come to a decision before I'd actually started cutting any metal. And a couple of other comments to make about it. You'll notice that the pictures are very incomplete. I mean, I haven't put the full details of the wheels in there, for example. There's no spokes because I didn't need them. I was only interested in looking at the overall size and proportions of the Loco. So the axles were important, the tires were important, nothing else really mattered. So I didn't put in more detail than I actually needed to do. So I'm not a person who makes pictures of every last detail of the locomotive. I only do as much CAD as I actually need to do, and I save time that way, or at least that's my theory anyway. So those are the reasons why you might want to adopt CAD. Now, before we get into CAD itself, something that's very important to know is that there are two distinct flavors. There's 2D and there's 3D. And they are very, very different. They're different in just about every respect that you can think of. So let's take them one at a time. And first of all, we'll talk about 2D CAD. Now, 2D CAD replicates the traditional process of doing a technical drawing by hand. So this is the one that's familiar to the past generation of draftspeople. When drawings were made in drawing offices on drawing boards by hand, then the results looked something like this. This just happens to be the general arrangement drawing of a Northwestern eight-coupled coal locomotive, which I happen to have to hand, but it showed the essential points that I wanted to get over. It shows the locomotive in a series of views. There's a view down the bottom here from the side, called, not surprisingly, the side elevation, and several views from the end, which are end elevations and sections. Elevations look at the outside, sections are cut on imaginary sections in order to show the inside details as well. So when drawings were made in that way, the person doing the drawing would do each of those drawings separately, and then the workshop could make the three-dimensional shape of the locomotive from that. And 2D CAD essentially replicates that process. So a series of views, elevations, plans that looking from the overhead, sections, each of them are drawn individually. The draftsman has to ensure that the views are consistent with one another. So that means that if the boiler is 6 feet in diameter, it's up to the draftsman to make sure that it's 6 feet in diameter in all the different views. Because if they're not, then the workshop is going to be seriously misled, or hopefully the drawing checker will pick it up and send it back to the draftsman with lots of rude words written all over it, which is usually what happened. 2D CAD follows exactly the same method. When people were designing 2D CAD software, that was the model that they followed. And they were able to add some refinements to improve the consistency and get over some of those problems, but it was still conceptually exactly the same process. Now, as far as modeling is concerned, if we do 2D CAD, it's to produce 2D parts. And 2D parts are the flat bits of the loco. So they're the frames, the stretchers, the sides of the tank, the motion bracket, the buffer beams at front and rear, all that sort of thing. It can also be what we call developed parts, like, for example, the boiler. If you're not making the boiler from a piece of tube, then you're making it from a flat sheet and you have to roll it. Now, you can draw it in the unrolled, the developed form, but you have to work out the dimensions for yourself. So you have to do a bit of arithmetic there. I don't think that 2D CAD really helps you in that process. I stand ready to be corrected, but when I was doing 2D CAD, we always had to do the unrolling process ourselves. Once you've done that, you can export the result in a 2D CAD format. The common ones are DXF and DWG. There are a number of others, but those are the two most common ones. And those 2D parts in a DXF or a DWG file can then be made by laser cutting or etching or CNC machining or the sort of CAM processes which are appropriate to making 2D parts. So here's an example. This is a frame that I drew. You can guess that it's a 240. I drew the frame and I put all the holes that I was going to need on it, and it was going to be made by a slot and tab sort of process that the same as etched kits are made of. So I was able to put the slots in and create a DXF file from that, get the frames laser cut, and there's the result that I got from the laser cutter, the two frames. And at the same time, I got a whole bunch of other bits and pieces made as well, cylinder front and rear, stretchers and other bits and bobs. But they're all the 2D parts that came from doing 2D CAD. Now, when we move from there to 3D CAD, the difference is right from the very start. The difference is in the approach. When you do 2D CAD, you're essentially replicating the manual process. You're doing side elevations, plans, end elevations, and building up the shape from that. When you're doing 3D CAD, you're working directly to create the shape in the form of what is called a solid model. So there's no separate views. We're creating that solid model from scratch. How do we do that? That's where the software comes in. A 3D CAD program will have inbuilt a number of primitive shapes, things like boxes and cylinders. A box is simply a rectangular box with a defined width, length, and height, and a defined location in space. A cylinder is a body with a defined diameter and length and a defined position in space. And we can build up complicated shapes from primitives like that. So as an example here, I'm showing the process of making an axle using 3D CAD. We start here with a cylinder. So we define the diameter, we define the length, we tell it that we're starting with a cylinder and we're telling it where it goes. It's aligned along that blue line there, which is maybe a bit faint, but there is a blue line along there which tells the program that's where we want the axis of the cylinder. Then we add two more cylinders, one there and one there. So we tell the program that we want a smaller diameter, we want a smaller length, and we want these cylinders coaxial with that one and located on the ends there, like that. And those give us the journals for the wheels. And then over here, assuming that it's an outside bearing, we add two more cylinders that will run in the outside bearings, and that is our axle. So basically three operations, and we've got an axle. If we want to put wheels on that axle, then it's a little bit more complicated because the tire of the wheel is a shape that's sufficiently complicated that we can't replicate it using boxes and cylinders and things like that. The tire has a defined shape. So what we have to do here is to make a sketch or a scale drawing of the tire to O gauge dimensions. And if you want to know what they are, then have a hunt through the Guild's knowledge base and you will find all of those dimensions available to you. And you can do a scale drawing like that, which this particular software package calls a sketch. And then you take that sketch and you tell it to revolve 360 degrees about a defined axis, and that creates the tire. Then we can add the hub, which is simply a cylinder primitive, and put a hole through it for the axle. And then a spoke is a box. So we know the length, we know the width, we know the height, we know the box has got to start at the outer surface of the cylinder here and finish at the inner surface of the tire there. And we don't have to go through that process for all the spokes because we can then tell the software, okay, we want 20 spokes and we want them evenly distributed around the circumference there, and one operation and it'll put them there. So that, in a very, very few words, is how you can build up a complicated shape from a set of primitives aided and abetted with sketches where you need them. And then from there you can carry on with as much or as little detail as you like. And here I've been building up the chassis of a tender. So I've got the wheels and I've got the frames and the stretchers and the beams at each end. And true to my philosophy of not drawing more than I need to, just about everything on that picture will be made by some CAM process. So the flat parts, the frames, the beams, the stretchers, stuff like that, they're all going to be made by 2D cutting, laser cutting, and the wheel centers and the brake blocks, 3D printing. So yeah, there's not a great deal of superfluous detail on that picture there. It's all useful, but it also means that I can make sure that everything fits together exactly as it should, and make sure that all the holes line up so that I can put the screws or the rivets or whatever it is through to hold everything together. So you can begin to see, I think, that the real object of doing all this CAD is to manufacture parts using CAM. So when we go from CAD to CAM, first of all, 3D CAD, it can produce 3D and 2D parts, as you can see. The difference is that you can do a lot more in 3D than you can in 2D. The 3D CAD, once you've got the model set up, like I've shown you here, once you've got that model set up, you can create solid model files for the different components, and those solid model files will be in a set format. The common ones would be STL, STEP, OBJ, and again, there are some others, but those are the most common ones. And those are the files which then go to the CAM process. And in the CAM process, there's likely to be some pre-processing before you actually get to the point of making something in CAM. But we'll talk about that when we get to the CAM stage. The point about it is that you need to know something about the CAM limitations and the CAM requirements when you're doing the 3D CAD. So this is where the two really do go hand in hand. When you're doing the CAD, you need to be thinking about how it's going to be made. That's actually an important part of the process. Very easy to design something that can't readily be made by any accessible method. Yeah, that's something that needs to be borne in mind. So, do we do 2D or do we do 3D CAD? Now, that's a question that people coming to CAD afresh will very often ask. Once they've realized that there's a big difference between the two, then an obvious question is, which one do you go for? Well, a few comments. First of all, 2D is much easier to learn, particularly if you've done some technical drawing in the past. You will find that adapting to the conventions and the requirements of 2D is much easier than 3D. So if you like, the learning curve will not be very steep. On the other hand, 3D is a much steeper learning curve. Sorry, there's no simple shortcut to that. I think everybody who gets into 3D CAD will find that. And knowing 2D CAD isn't really a benefit to you. I mean, some people will say that the first thing you have to do is to forget everything you knew about 2D CAD. Well, I think that's probably a bit of an exaggeration, but there's probably some truth in it, actually. It is a very different way of doing things. So you have to give yourself time to learn it. Sorry, but that's the way it is. On the plus side, 3D will do everything 2D does and a lot more besides. So when I got into using CAD in my modeling, I started off doing a lot of 2D work, and later on I got into 3D CAD, and now I don't do any 2D CAD at all because I know I can do everything in 3D CAD, and it works perfectly fine for me. But ultimately, it's your choice. It depends on what sort of parts you want to make. Do you want to make just the flat parts, or do you want to make the more complicated parts? And each person will make their own decisions about that. If you just want to make the flat parts, then you don't really need 3D CAD. Another question What's the best CAD package? Now, this is one of those questions that every few months or sooner than that, somebody on a forum will say, well, what's the best CAD package for me? In the hope that everybody is going to reply by saying, oh, you really must get XYZ. It's the only one to use. What happens in reality is that you get 6 answers from 6 different people who all advocate 6 different CAD packages. And at the end of it, nobody is any the wiser. It really doesn't help. And that's because it's usually the wrong question to ask. If I'm asked that question, the only answer I can give is some variation on what it says there. It's the one that you are comfortable with and does what you want to do. And I deliberately emphasize you because what works for me may not work for you. Picking up on that second point, does what you want to do. Well, if you don't know what you want to do, you are probably not ready for it. I know that people will say, and they have said to me, well, I just want to play with it and find out what it can do. The reality is that if you just play with it, you will almost certainly get frustrated, you'll give up, you'll get, and you'll go away, and you won't find out what it can do because you're at the bottom of the learning curve. And it's tough to begin with. You really do have to think it through first. Not in great detail, but at least you have to have some idea of what you want to do with CAD. And that's why I've been at pains here to explain the sorts of things that you can do. And what's important to you will be different from what's important to me and what's important to everyone else here. It is a personal decision, but you have to think about the hobby, what you want to do, and whether CAD is the best way to go about doing it. Once you've got to that point, then you can try it and see. So you have to think about it first, then try it and see. And most of the software packages do actually make that feasible for you. Some of them are free. Some of them are free only to hobbyists like us. Some of them have a free dumbed down version, which leaves out some of the more complicated features that you may not need anyway. And even the ones that you have to pay for will very often have a 60-day or a 30-day trial period where you can try it out for free and just get a feel for what it's useful for. And that means that you can download and play around as much as you like, and that is how you find the one that you're comfortable with. Now, people do get terribly concerned that some of them have features that others don't. That's not entirely a myth, but it's not entirely true either. It's a very competitive business out there in the real world where they're paying serious money for these packages and designing airplanes with them. It's very competitive, and all the packages all have very, very similar functions. They will all do pretty much the same thing. There are nomenclature differences. They call things by different names. They do things in slightly different ways. But if you prefer package X to package Y, chances are you're not going to be missing anything that's important. So you can actually choose. A few years ago, when James was creating the knowledge base on the website, I put together a page on that knowledge base, which was comparing the different CAD packages. And I think the information there is still fairly current. So if you want to take a look at that, just go on the knowledge base and follow the links to computer-based modeling and introduction to CAD. Um, and I just did what I've just said. I downloaded all the packages I could find and I tried them out and I got a feel for them, just so that I could summarize them. So if you're at that stage, then do take a look at the knowledge base, and that'll give you a, a way to start. Okay, so that's enough of CAD. I hope that's at least given you some overview of what it can do and how it can help you and some of the obvious traps. Um, let's move on to CAM. And here I'm really talking about the sort of CAM tools that we can use. So these are not the CAM tools that Ford and General Motors will be using for making motor cars or British Aerospace for making airplanes. That's a different level entirely. This is very much focused on the sort of stuff that we can make model railway engines from. And I'm going to talk about the ones that I use because they're the ones that I know about. So I'm going to leave out a few. If I'm leaving out your favorite CAM technology, I'm sorry. I don't wish to offend anybody. I've just left it out because I don't know enough about it. Have a word with James and see if you can do a presentation in some future meeting. Those are the ones that I have been using in the past few years. So laser cutting of metals, 3D printing of both plastics and metals, and CNC machining of metals. And the the box at the bottom, I think, is important. Some of them can be done at home. Some of those I have done at home. Some of them need professional equipment. And for very good reasons, it may not be appropriate to do some of those things at home because the equipment may be horrendously expensive, or it may require things like high temperatures or obnoxious chemicals, or, you know, the sort of things that really make it impossible to use in the domestic environment. Which isn't to say that those technologies are not available to us, because there are people who will offer their services, even for one-offs. If you go on the web and if you do a search, you will find companies offering their services. They allow you to upload a CAD file and you can check it out online. They'll give you a quote online, and then you can either accept or reject. And if you accept it, then within a reasonable time through the post or by courier, a nice little package arrives. So first off, laser cutting metal. This is one of the ones that you really don't want to be doing in the spare bedroom. It uses high power lasers, it generates a lot of heat, and yeah, it's altogether very unsafe if you don't know what you're doing. Laser cutting at home is viable if you're wanting to cut thin plywood or plastic sheet or material cardboard, materials of that type. If we're dealing with metals, it's a different ball game. It only creates the 2D shapes. You can make the frames and the stretchers and the motion brackets and stuff like that using 2D technology. And I've had parts cut in mild steel and in stainless steel. I haven't had parts cut in brass or other copper alloys. That includes nickel, silver. It's actually more expensive, not just because the alloy itself is expensive, but brass and copper alloys also demand a greater laser power. It's because the metals are more conductive of heat, and so they have to turn up the laser power, and the cost goes up. Um, People tend to raise their eyebrows a little bit when I say I use mild steel. I actually like mild steel. It's soft enough that I can work it perfectly all right. It's hard enough that it doesn't deform with the occasional knock or ding. Um, and it soft solders very well. Um, so the only real downside from my point of view is that it rusts. And if you take precautions to prevent rusting, it does mean you have to clean it and dry it and, do things like that. I would say it's actually a very good modeling material. Stainless steel is something else. It's all right for one-off components that you don't need to solder to anything else, but it's a bit difficult to work. 3D printing in plastics. This is the CAM technology that most modelers are probably most familiar with. A lot of people these days have home equipment um, available for a few £100, which generally enable you to print um, soft plastics, thermoplastics, PLA, PETG, things like that. Um, some of those machines are now available for printing hard plastics, nylon and plastics of that type, but I think that still mostly requires professional equipment. From my point of view, I prefer the hard plastics because they're more durable. Um, and I that to me seems to be something that's important. But anytime we're using plastics in the context of loco building, um, strength and durability are questions that we have to think about. Also, things like UV sensitivity. If I leave it out in sunshine for a long time, is it going to either deform or degrade, become embrittled, something like that? Um, I think there are some significant downsides. I know people do use them. I use them myself, but you have to be aware of the issues there. Um, Here's an example where I've had printed in a hard plastic a wheel center, a driving wheel, quite obviously, and the picture on the left-hand side is the STL file, the solid model file that I generated in CAD using those cylinders and box primitives and all the rest of it. Um, and that is the wheel that was printed for me. I didn't do it myself. It was printed by a professional printing concern. Um, and people have questioned whether the strength and the durability of a wheel center like that one. Um, when they do, my answer is that you're familiar with Slater's wheels. Well, they use a nylon center. Okay, it's in their case, it is injection molded, whereas this is 3D printed, but essentially it's very similar material with very similar physical properties. So if you're happy with Slater's wheels, you should be happy with 3D printed centers. And so far, early days yet, so far I haven't had any problems with them. Uh, Here's some more, some boiler fittings, chimney, dome, safety valve cover. The boiler back head was a complicated thing to draw because it's got lots of different components to it, but I was very pleased with the way it turned out actually because it's I managed to capture a lot of the detail of the firebox door opening mechanism and all that sort of stuff. So yeah, there were quite a few hours at the computer drawing that, but I thought the result was worth it. Some things don't work. This is the original motion bracket, which was 3D printed in nylon. It's the bit that these lugs here, they support the slide bars, so the crossheads go through there and the valve gear goes through that hole there. Um, it looks nice. It's got all the prototype details, and it just wasn't sufficiently rigid. It used to flex about, and when you're holding slide bars, that's a bit of a problem. So in the end, I decided that it just wasn't up to the job, and I had to scrap it and replace it with a custom part made from metal in the traditional way. Um, but that was a learning process. I also started off with 3D printed horn blocks on the driving wheel and the trailing wheel, sorry, the leading wheel of that loco. And again, they just weren't rigid enough. There's individual springs on each of those wheels, and the horn blocks would deform under the action of the spring. And I didn't actually have one break, but I could see that they were going to break before very long. So it was an experiment worth doing, but I decided that for operational parts like that, where you actually have things moving and you have forces involved, then that sort of material is really not going to be the right one. For what I call passive components, which don't actually do anything except look nice, it's perfectly fine. But for operational components, no, my experience has not been good. 3D printing of metals. Some years ago, I got some tender springs and axle boxes 3D printed. Wasn't cheap, but I thought it was worth it. I thought the results were very, very good. Um, that sort of 3D print technology has disappeared, and I think I understand the commercial reasons for it, but today I don't know of any company that's actually doing 3D printing in brass. If you want stuff made in brass, you can do a 3D printed wax and use that as the basis for investment casting. And there are people who offer that facility, but it becomes a two-step process and you're dealing with two different companies, unless, of course, you're doing the 3D printing of the wax yourself. Where I think 3D printing of metals is a useful thing is in stainless steel and aluminium. Mild steel is difficult to 3D print for technical reasons, which won't be overcome anytime soon. But stainless steel and aluminium, readily available, many people can do them. In many cases, they are cheaper than other materials. And if you're dealing with something like a wheel center, for example, where you're not going to want to solder it to anything, I think that they have a very good place. This presentation comes at the wrong time because I'm in the process of doing a wheel center for a new project, which I'm intending to get 3D printed in stainless steel just to see how well it works. So come back in a few months and I might be able to update you on that one. But I know that there are people in the larger scales and in the model engineering scales which are starting to use 3D printing in those materials. So I think I feel fairly confident about it. but brass, not so sure. And I I put this slide on because I'm pleased with myself that I've got a CNC milling machine that you can see on the left there, which I partly built myself. Um, I can tell you the history behind it if you like, but suffice to say that it's up and running. It's only a very small machine, as you can see, but it has produced parts like these. What they called. Anyway, they're injector control handles. They're machined on a stick of brass, and I cut them off along a line there, and then put them in, solder them in place on the model. And this is a dome that was done by CNC machining. And that's a photograph of it coming straight off the dome, and you can straight off the machine, and you can see that there are still a lot of machining marks on it. So it still needs some filing and polishing before producing that. But you can see that the difficult thing, which is the shaped flare where it goes around, where it wraps around the boiler, has come out very nicely that way. And I mentioned pre-processing. This is the dome or half the dome, and the pre-processing is necessary to go from the solid model file to produce a tool path, because with CNC machining, you have to tell the tool the path to follow. And that's a function of the software. So here, the blue lines are the lines that the tool followed, and that's the reason why you've got those lines on the machined part there. And that's all done in software as well. There are a lot of different toolpath options. To produce that dome, I had to try several different toolpaths until I found the best one. So again, it was a learning process, but it really reinforced the conclusion that if you're going to use CNC, it does need a proper combination of software and hardware. And I think that's more true of CNC than it is of the other CAM technologies. But I'm not expecting many people to go rushing out and buying CNC machines anytime soon. I just thought I'd throw that in to show you what I've been spending my time on over the last few months. But for producing parts in brass, since I can't 3D print them, I'm very hopeful that this is going to be a way of producing those nice brass fittings that old time locomotives used to have, because I don't think there's a way of printing a polished brass dome in plastic and then painting it to look like polished brass. I think the only thing that looks like polished brass is polished brass. You may differ with me from me, but that's my view of it. So there we are. A quick run through, but I'm got a little bit of time left. So thank you very much for your attention. And if there are any questions, I will do my very best to answer them. So back to you, James.
Thank you, Nick. Thank you very much. We've had a comment from Graham who said that he did use Fusion, but changing conditions from the manufacturer of Fusion led him to Solid Edge. But they changed their terms and cut him out, so he's now learning FreeCAD.
Okay.
FreeCAD, he said, had a poor reputation, but it's been upgraded.
Yep.
Changing terms and conditions from commercial organizations is his concern. And I can understand that, because Fusion is free, but there are limits on how many drawings you can have at a time.
No, there's no limit on the number of drawings.
Well, it's a limit to the number of editable drawings.
Yeah, that's right. Yeah,
But
yeah. You
you're right.
you
It
Yeah,
doesn't really make much difference.
you have to go dancing around and turning off the editing of the ones you're not working on today, and
Yes.
yeah, it's one of the less pleasant aspects of it. But
Yep.
from Autodesk's point of view, I can see exactly why they've incorporated it.
I think.
Because if you're working in the commercial environment and paying hard money for their product,
Yeah.
it would be a real pain.
Yes.
Um,
Absolutely.
so, they want to make sure that if you are using it commercially, you're going to pay for it.
Yep.
So, yeah, I entirely understand what you're saying, and as I say, it's a personal decision.
Yeah.
Um, but yeah, I know Fusion, Solid Edge, FreeCAD. They all do very much the same sort of things, so I'm quite sure that you can produce decent results with any of them.
I think with Fusion, one important thing is because it's cloud based, is
Yeah,
to make sure you save your drawings onto your own machine. So export them as a F3D um,
you,
file. So at least you've got your own copy if anything happens to it in the future.
yes, you have, but on the other hand, um, I don't see a problem with it being cloud-based. I mean, all Fusion users use the cloud. So those big companies that rely on Fusion for their livelihood, their stuff is in the cloud as well. And if
Yep.
they weren't very, very confident of preserving it, they wouldn't use it.
True.
But okay, if it's stored in the cloud, it's going to be stored just once, but on several different servers in several different locations around the world.
Yeah.
So even if one server were destroyed by an earthquake or whatever, you wouldn't lose your files.
Yeah. True.
If, heaven forbid, your home were destroyed by fire or flood and you lost your computer and you lost your backup drive, you'd
Yeah.
be stuck.
You would
I,
indeed.
I would argue that cloud storage today is actually more secure than personal storage.
Probably true. Yeah. I was thinking more from the point of view that if Fusion decided that they were going to force you to pay um,
Yeah,
to
I would
continue, at least you've got a copy.
well, I would hope that they would give sufficient warning that you could download everything before
Yeah. Good
that
point.
happened.
You should do.
Yeah, but
Um,
yeah,
if anybody would like to,
it's true. Yeah.
yeah, if anybody would like to ask questions, by all means, unmute yourself and ask away. Otherwise, we're at the end of our time slot. So I'll wait a little while, see if anybody wants to ask a question. No, not at the moment. Okay, well, I'd like to thank Nick very much indeed for his
Yep.
talk. I found it extremely interesting. And obviously, this will be available on YouTube, on the Gajo Guild YouTube channel, once today is complete and we've had time to get the recording and check it out. So anyway, thanks again, Nick. Thank you very much.
Okay, thank you very much. And I hope that you found it interesting and maybe even useful.